Like one of the things I just wanted to like um, this thing player A is always trying, like the first player is always trying to maximize its rewards, and second player is trying to minimize its reward. Okay, so and the aggregate reward in a zero sum game is always zero. So like then why exactly player one tries to have a minimum of maximum in
Okay,
in secure
I'll
strategy?
come to that. Don't worry. That's anyways like the key point in the whole lecture this time. So I'll come to that. Okay. So good evening. This is week 3 of the tutorial session in games and information. I There was someone who wrote that they have a doubt in quiz 2, so I can take that first and then I'll start with week 3. So yeah, was it Vivek? You can ask.
Yes, madam. Actually, in the quiz too, one question, the answer which is given in the solution and the answer in the what we have given, that was differ actually. So I don't know which answer is correct. So whom I have to inform for that?
Oh, just drop an email.
Okay, so my ID.
Just drop an email. Which ID have you been writing to mostly?
Actually, we are getting that to exact the course coordinator, no, not course person. So who I
Yeah,
have to
so it's the TAs of the course who will respond to it. So if whatever you're saying is actually true and there is a discrepancy, they'll fix the discrepancy. So it might require either changing the answer key or require
Okay.
updating that particular answer of the question. So as long as it's not it, just because of whatever is given in the solution doesn't become ambiguous, they'll make the changes. That's not an issue. So just write an email
Okay.
and mention
Okay.
exactly what is the issue. Might have missed it.
Okay. Okay.
Not
So,
a thing.
if possible, maybe by before end of the session, you can provide the mail ID if possible.
Email ID. Okay, I'll have to check that. Yeah.
Yeah. Thank you.
Okay.
You can post in Q&A section, right? The thing is, you can then click on, when you open your course, then there is a Q&A section. You can click that section and you can just create a new conversation there for the doubt. Have you written that?
Okay. Okay. I will check. So in the general question and answer.
Yes, there is in the menu bar you have Q&A. You can click
Okay.
Q&A,
Okay.
and then you will go to a Google discussions page where you can create a new conversation, put your doubt there, and you will be responded by the email. That is basically what we are doing since like last
Okay.
several courses.
Okay.
That's
Okay.
fine.
Thank you.
Okay. So let's get started. In the last two sessions, we have talked about very simple things. We started by talking about. Sorry, one second. We started by talking about what a game is, what is a Nash equilibrium, the concept of it. We talked about dominance, dominated strategy, dominant strategy, and so on, and how can that concept or that idea be used to find the Nash equilibrium if it exists in a particular game. Then, to further make things more formal, we talked about what is the meaning of something that is known to everybody or what is common knowledge. So, to be able to talk about common knowledge, we studied the Omen model, which basically focused on what is a knowledge operator, which tells us, given a particular event, what does player I know about that event? What does player J know about, let's say, player I knows about that event, and so on. So it's a recursive thing, and it can be written down. And with that, we defined what in this model what is called as common knowledge. Then we saw a few theorems related to common knowledge the knowledge operator, and the connected component that allows us to find if something is a common knowledge or some event can be a common knowledge in a particular setting. This was all with the scenario where there were no beliefs in the system. Then we talked about what happens if there are some beliefs in the system, meaning some the players know what is the probability of getting any particular state of the world, and that is like a prior. It's known to everyone. It's a common prior. With that, we talked about how can, in such scenarios where there are beliefs, what happens to the knowledge operator, what happens to first level beliefs, second level beliefs, and so on. And can there be a concept of, is there a concept of common knowledge here? We talked about that, and there was a theorem we ended with. So today we're going to talk about a particular class of games, which is zero-sum games. In these particular games, there are a few very nice properties that come up, but these properties are actually general and can be used in other games also. So we'll study all of these things today. Okay, so a zero-sum game, from the name itself, tells us it's a game typically between two players, and it's a game in which the utility of, let's say, player 1 will be the negative of the utility of the second player. So typically when we made the payoff matrix, we wrote down what was the utility of the first player, then the utility of the second player for each strategy. So it was for each x1, x2 value. And we made the whole matrix of that. So if suppose we had a simple scenario of, say, two strategies for each player, then it was a payoff matrix of this kind. Some a1, a2, b1, b2, some values, doesn't matter what, and so on. But here, since there is a very specific property for the utility function itself, we don't have to worry about both a1 and a2. One is enough to tell what the other one is. So the payoff matrix that is generally written tells us the payoff or the utility of agent 1 or player 1. So that is written in this form. Player 1 is the one who chooses the row, and the one who chooses the column is the player 2. So what we write here is, let's say any one of them. So let's say this is the ith row and jth column. So aij is the utility of player 1 when the strategy played is, okay, maybe I can just write the strategy this way: ith strategy by first player and jth strategy by the second player. That's what it means. Is there a question or? Hello. Okay. One thing that you have to be very careful about, especially in this lecture, is that you should remember everything has been defined with the idea that player 1, the row player, is minimizing and the column player is maximizing. There may be a situation where it's the opposite that is happening, and it might be given in a particular question. You will have to rethink the definitions with respect to the question. So you have to be careful in that particular part. Okay, so remember this. whatever I'm going to talk about, unless I say that player 1 is maximizing, you can just assume everything is said in a way where the row player is the one who is minimizing and the column player is maximizing. Maximizing means it's just trying to find the largest value from the values it can see. So from the matrix here, whatever aij it gets, it's trying to maximize that, which in turn makes its own value, the negative of that, minimize. So in that sense, it's fine. They're doing the exact same thing. Okay, so now that we have like the basic introductory thing as to what a zero sum matrix is or what a zero sum game is, let's talk a little bit more about this matrix A. So let me ask a few very simple questions. I assume you should know the answer already, but nevertheless. So what kind of properties do we expect from this matrix A? So first point, does it have to be a square matrix? Anyone?
Yes, it should be a square matrix. It may not be a square matrix because the number of strategies of both the players might be different. So it's m by n.
Exactly. It doesn't have to be a square matrix. Reason being, strategies of the players don't have to match. So there is always a possibility that the strategies of player 1 are just 2, and for the other one, maybe there are 3 strategies. Nothing is stopping us from dealing with a situation of that kind. So this doesn't have to be a square matrix. Okay, then anything about the entries in the matrix? Do they all have to be positive? Do they all have to be greater than 0, greater than or equal to 0, or something like that?
The aggregate sum should be 0, I guess.
That is there, but the matrix that we will get to see is going to be just this. It'll have just the utility of one player, player 1. The utility of the second player is anyways not visible to us. Those two will be by default summing to 0. That's for sure there. But it never says that any of these entries has to be a certain value. It has to be greater than 0 or greater than equal to 0 or anything like that. So there are no restrictions on what kind of values are allowed in this matrix. This is just a kind of a utility function itself, and there are no such restrictions on A, the entries of A. Okay, and similarly, there is nothing to be said about eigenvalues, that there has to be whatever. There's nothing to be said about eigenvalues or typical properties that you'll have with a matrix, because here it's representing something very specific to our problem, and depending on the problem that we are discussing, it can be easily adjusted to that. Okay, so the point here is, when we are dealing with a game which is a zero sum game, the players would have their own objective, minimize or maximize, whichever player we are talking about or what matrix we are looking at. What they actually choose, we saw one concept of how they can choose an equilibrium strategy, right? We saw the way of coming up with dominated or dominant strategies, and using iterated process of looking at those strategies, we saw how to find the Nash equilibria. That was one way to reach the Nash equilibria. Now in this particular type of game, one more thing comes up, which is what will be the focus in today's tutorial also. But anyways, before we get to that, let's take a simple example. So let's say I am being given that this is the utility matrix. So rows represent the strategies of P1, okay, and the columns represent the strategies of P2. So this is for P1, this is for P2. Now from here we can see that this is an example where the first player has 2 strategies while the second player has 3 strategies available. we can try using the concept of Nash equilibria here and see what happens. Does anyone recall how do we find the Nash for any particular scenario?
By elimination of dominated strategies, weakly dominated strategies.
Okay, we can do that. So, let's recall that this is the minimizing player. So, is there any strictly dominated strategy here?
The second row is like strictly, it is weakly dominated now. It is not strictly because it has 3-3, so it's weakly dominated
Okay,
by the first
you
row.
can't compare this and this. The
Yeah.
comparison should always be between utility values for the same strategy of the other agent. You can't change the strategy of the other agent, right? So you'll be looking at these two. If you compare these two, 3 is better. But if you compare these two, 1 is better. So here we can't find something strictly better. So it doesn't look like there is a dominated strategy for player 1. Maybe we can look at player 2. Player 2
Row
is
1, sorry, column 1 dominated.
No, also I don't think there is a strictly dominated strategy because like in the corresponding ones are not like
the dominant one has to be the best one. So player 2 is maximizing here, okay? That means it will compare, is the strategy here better than all the remaining ones? So is 2 better than 3 and 4? It's maximizing, it's not. 3 is definitely better than 1 and minus 1, but this is not. So this is not the dominant strategy. So that elimination method will not work for this example. What we can do is we can just simply go through the whole matrix. So let's say we fix any one strategy of, let's say, player 2 and compare the utility of player 1 and mark the smaller one because player 1 is minimizing. So this one. Similarly for the other ones. And we can repeat the same process but this time for the other agent. So now I'm looking at these 3. So whatever is there in row 1, and I'm trying to maximize it and highlight the maximum one. So in this particular example, what happened is nothing got highlighted twice, meaning nothing is the right thing for both the agents. So actually this doesn't have a Nash equilibria or even an equilibria concept in general. Or rather, in pure strategy, it doesn't have. Okay, so we'll look at one more way of trying to find if there is a Nash equilibria or a concept of a solution in specifically zero-sum games now. So that concept comes about by looking at security strategies. Now, before I go into the math of whatever all of this is, all this security strategy is saying is each agent, each player would want to make sure that they get some amount of payoff. So let's analyze this example again. Let's say
In the example, I have a doubt. In the row, in the P1 is a minimizer. So in the row, we have to choose the minimum value. No?
Yeah.
So you have chosen 4 in the row.
No. This is what I have to choose from. Player 1 is choosing a row. So given a column, it's looking at which row should it be choosing. So for that, I've highlighted 2.
Thank you.
Yeah. Okay. So now let's look at this example a bit more carefully. These numbers don't have much value, but there is a point to be made. Suppose we're not trying to look for a concept or a solution here. Clearly this doesn't have one, so fine. But suppose we say that okay, player 1 decides to play row 2. Now he can get three possible utility values. He can either get 3, 1 or -1 depending on what was chosen by player 2. Right? It would prefer, player 1 would prefer if he got minus, well, he would prefer if he got -1 or even 1, because that's at least better than, that would at least say that he has taken the right strategy. But what if player 2 chooses row, not row, player 2 is going to be choosing columns. So what if player 2 chooses column 1? So now what happened is, I'm saying this is the one that got chosen. Player 1 chose this and player 2 chose this. In a scenario like this, the utility that they got was, utility for 1 is 3 and utility for the second player is -3. But seeing this, player 1 would say, it might have been better if he had chosen a different, if he knew. So if by chance he knew what was going to be chosen by player 2, he could try and adjust what should be his choice. So here, if he ends up choosing row 2, he is getting a utility 3, which is much higher than what he would have gotten in any other scenario. This is not the best that he would have gotten. So if by chance, if instead he says that okay, no, I want to go for row 1. In row 1, the possibilities are 2, 3, 4. Now, just compare the possibilities available in these two scenarios. Just by numbers, and I'm no longer talking about comparing based on strategies, just by numbers. Clearly, the worst one is available in this, in strategy where player A has chosen row 1. If this gets actually chosen and player 2 ends up taking this strategy, he would have the worst payoff possible in the whole matrix. So security strategies are trying to avoid such a scenario. They're trying to minimize the risk of their own utility getting to a high a value given what the other would have chosen. That's roughly what is the objective of trying to do this. It's trying to ensure whatever utility player 1 gets at the end, it's not the worst one available. He's trying to find something secure, something stable. And that's the idea in looking into these security strategies. So what he would do is, so let's look at this example itself. So what player 1 could possibly do here is, okay, maybe I'll just write it again. So he can be like, okay, let me see what is the worst I can end up in. Which strategy, if chosen by the other agent, does the most damage? See, if a player is trying to minimize, for him the most damage would be something that is maximizing. So here we'll look at maximum in the column. So we're fixing a strategy. So we're fixing the strategy for player 1 right now. So let's say we're fixing row 1, and then we're looking at, from all these different values, which is the worst possible value that could have gotten chosen for him. So that is just looking at the max of these. So more carefully, I'm looking at the max of Aij where I have fixed I have fixed the row, and I'm looking at the max with respect to j. As in, which strategy chosen by the other agent would cause the most damage to my utility. That's what this is saying. So in that case, what I would get is, so let's say I've fixed this row. From 2, 3, 4, the maximum is 4. Now I'll repeat the same thing for the next row. So from 3, 1, minus 1, the worst is 3. Now, if the player is supposed to just try and make sure he is in a secure position, he's avoiding the worst case scenario, what strategy should he choose? So in that sense, the security strategy or the safe strategy, which at least avoids risk of getting the worst possible payoff for him, would be to choose row 2. Which, so what we have done here is now we have taken a minimization over whatever was the maximization done by the other agent. Are you able to follow what I'm saying? I have not gotten into the definitions yet, the precise things yet, but still it's coming out from the example itself. So now I can repeat the same thing for the other agent. Now remember, the other agent is trying to maximize. So for him, the most damage would not be in terms of maximizing, it will be in the form of minimizing. So let's say what's the worst player 2 can end up with. So for that, we'll look into the minimizing the column or the row values, minimizing the row values, meaning I am asking, I have fixed a particular column. So let's say I fixed this column, and in that column, I am just comparing which is the worst choice with respect to player 2. Then what we see is here we're supposed to take the smaller one basically. So the smaller one here is 2. Smaller one for the next column is 1. And for the last column, it is minus 1. Now, after he has seen what are the worst possible scenarios, all he is going to do is his own objective function, which is to maximize. So from these, he'll say, okay, the safest bet for me is to play the strategy, to play this strategy, or play the strategy which gives me this, meaning it is column 1. So what this player actually ended up doing is it took a maximization of this worst case scenario. Okay, this got a little messy. I'll clean this up in a minute. But yeah, so let's take a moment and see if any more doubts in this part.
Ma'am, from the second player's perspective, column 1 and column 2 both are like similar or not?
See, we are right now looking at it from the perspective of avoiding the worst case scenario. That's what security levels mean, or security strategies means. So in that sense, they are different. If he ended up choosing this column, the worst he could have gotten is 1. But if he chooses this, the worst he would have gotten is utility 2. So this is better than having chosen this. I'm not saying, right now we have not reached a point where we are saying that security strategies are a solution concept. Right now we are just saying this is a way to avoid risk of getting the opposite of whatever your objective function is. So what kind of strategies can you choose with that in mind?
So here what I'm saying is like both players are trying to just counter each other. They are not trying to maximize their reward like we found in Nash equilibrium.
Yes.
That everybody was trying to optimize its reward. But here what I'm saying is like everybody's trying to like it's like a fight where he's trying to cause more destruction to the other player as possible rather than this reward for the player himself.
Yes, that's why it's called a security strategy or a security level.
Thanks, ma'am.
it's sort of trying to make sure that they don't end up in the worst case scenario.
Okay. Thanks, Pep.
Yeah. Okay, so now let's go through it in a slightly more formal way. So I'll erase some of these things and keep only what I need. Okay, so two things that are useful that came out from here are the following. This is one, okay. And this is the other one. Now, we could look at the same thing in a slightly different way also. We can look at it in terms of inequalities. So, this is with respect to player 1. Player 1's original objective is to minimize the utility, but he's trying to mitigate the scenario where he might end up with the worst possible utility, because there is a different agent involved and they're as strictly non-cooperative as possible. Their utilities are exactly opposite. Their In that sense, their objectives are exactly opposite. So there's a risk here. So he's just trying to mitigate that risk, and in the process of doing that, what he's basically saying is a security strategy is basically, for player 1, it is any strategy which is such that if you were to take the maximum with respect to the column for any of those values, keeping the row fixed, then whichever row gives you the least possible value is the security level. So it's, in other words, like saying the argmin of this is I star, which is what this equation is also saying. So this object is called as the security level for player 1. This is min max. Okay, now if we were to look at the same kind of object for the other player, we would be asking similar kind of a question. So we're asking, okay, in this scenario, the player's objective is to maximize. Hence, he wants to make sure he doesn't end up with the least possible utility. So he's trying to maximize the utility, but at the same time, he's trying to ensure that he doesn't end up with the worst possible scenario. So he's looking at the minimums while keeping his own strategy fixed, and changing the strategy of the other guy. And he's saying, I want the strategy which gives me the maximum from these worst scenarios. That's what this is. And hence this J star is the argmax of this quantity. And hence we can also define a security level for player 2, which is now, instead of being min max like for the previous player, this is max min. Okay, so I hope at this point you can understand what security strategies and security levels are. We'll take a couple of examples to understand this better, because this, even though we have only talked about it in the case of zero sum games, this is actually useful in general games, as in general for non-cooperative games. Okay, so now let's take an example. I think this is supposed to be 4. Okay, so now what are we supposed to do? First thing that we are told is, okay, it's the same convention. So player 1 is minimizing and player 2 is maximizing. So if player 1 is minimizing, he wants to ensure that whatever he gets keeping his strategy fixed and the other player's strategy changing, he wants to make sure he doesn't end up with the worst case scenario. So what he'll be looking at is the max from the column. So he's looking at max of j aij, which is max between these quantities in a particular fixed row. So for the first one, he'll get 5. For the next one, he'll get 3. And for the last one, again, he'll get 5. So his objective is ultimately to find the minima of these 3, right? Which is just minimum of 5, 3 and 5, which turns out to be 3. And the strategy which did that, I star, is the row 2. So I'm saying that this is 1, 2, 3, this is 1, 2, 3. Not computer science convention, just standard convention of calling rows and columns. Okay, so this is for player 1. We can repeat the same thing and do it for player 2 as well. So if we do it for player 2, now remember player 2 is interested in maximizing his own utility, which means as a security, he wants to make sure he doesn't end up with the least value from the whole table. So what he will do is, he will minimize, keeping his strategy fixed, he'll minimize which strategy of the other agent gives the minimum utility. So he's minimizing with respect to I of that quantity. So that is, so he's minimizing between these 3, which gives me 3 here, 2 here and 1 here. And ultimately he wants to choose the best of the available option. For him the best would be maximizing these. So he would take a maxima over 3, 2 and 1, which gives him 3. And he got that for I star, not I star, j star, the column equal to 1. So see what did they end up choosing? Player 1 ended up choosing this column and player 2 ended up choosing this column. There's one point which is common to both of them, and that is, or there's like a common strategy, which is this one. So as a strategy, they will end up choosing, if they play security levels, if they play security strategies, they would get utility 3 and -3. Now let's check if this really is the equilibria of the game or not. So we can try and see the Nash equilibria of this game. So we can just repeat the process of, looking row wise and column wise and so on. So first step, fix a particular strategy of the other player. Let's say we are looking at player 1 right now. So we are fixing the strategy of player 2. So we look at one column at a time and compare the rows, because player 1 is the one who's going to play a strategy, which means he's minimizing between 4, 3 and 5, and the minimum would be 3. Similarly, he can go to the next column, meaning the next strategy that the other one can play, and again minimize from there. So he's minimizing between 2, 3 and 3, so he ends up choosing 2. And similarly, and the last one, he'd end up choosing 1. This is for player 1. Now player 2 would repeat the same process, but just in this way. Player 2 would fix the row and then search over the columns, and his objective is to maximize, so he'll go for the maximum one here. So he'll choose 5 from 4, 2 and 5. Next, between 3 and 1, now because of the presence of 3 and 3, he'll choose both of them. And last, he'll look at the last row and again choose the maximum one, which is 5. So now you see both of them ended up choosing this particular value or this particular case. So it turns out that this Nash equilibria of this game is actually getting chosen by playing the security strategies also. If you recall, this was already explained in the uh, there was a theorem or a corollary that was talked about in class. If this VA security level of player 1 is equal to security level of player 2, then there will exist a saddle point. If there is a saddle point, then security levels or the strategies created by the security levels are themselves going to be useful to define the equilibria concept in that particular scenario. And that's exactly what happened in this example. But don't worry, we'll come back to this example once we have seen that theorem one more time. Okay, any doubts in this? Okay, now because this is something that you will face, the convention of which player is the minimizing one, it keeps switching from textbook to textbook, from people to people. So you have to be careful with change of definitions also. So let's take that opposite scenario. Okay, I'll come back to saddle point after I've introduced it more carefully again. So let's take this scenario. Here, player 1 is maximizing, player 2 is minimizing. And the utility that is given to us by default is of player 1. So, same as before, we would fix a strategy here and look at what are the three things, what can be played by the other agent. But in the process of doing that, now our objective is maximization, meaning the opposite of that is what we are trying to mitigate. So we'd be looking at minima with respect to j of these values for a fixed row. Okay, so now we are sort of minimizing through the columns. So that means we would look at these three values and say, okay, the minimum is 3 here, 1 here, and 2 here. And for player 1, the idea is ultimately to maximize even from the worst possible scenarios. So he would say, okay, that means I should go for this one. So his security level would be 3. And this is happening for I star equal to 1. And that's the security strategy for him. So this is what he chose. Now, same thing will be repeated by the other agent. Now, the other agent's objective is to minimize, meaning he's going to avoid getting the maximum utility value. So here he'll look at the max of I of this Aij. That means he's fixing a j and looking at the different row values for that given column, and then just choosing the minima from there. Is just choosing the maxima from there. So the maxima here would be 5, 4, and 5. And this player wants to ultimately minimize. So he's going to choose the minimum of these values, which means he's going to choose 4. So J star is equal to 2 here. Now, see, in this scenario, the security level of player 1, I don't want to confuse you with notation. So just because I have a opposite scenario where player 1 is maximizing, so let me call his security level as V1, and for the other guy it's V2, and I'm not using the same notation as before. I'm restricting this notation to mean for the convention that we are using in the tutorial and even in the lectures. Okay, so now here V1 and V2 are not equal. And we know if the security levels are not matching, meaning the value of the game, we can't define a value of the game here, then typically a saddle point does not exist, or in fact, a saddle point does not exist in that scenario. Another way of looking at the same thing would be to look at the Nash equilibria of the game. So let's see if we can find a Nash equilibria of the game, if that exists or not, and then make this make this statement slightly more strongly. So we could do the following. So now I'm looking at the Nash equilibria, okay? So to find Nash, what I'm supposed to do is fix a strategy of the opposite guy. Let's say I'm right now focusing on player 1. So I'm fixing the strategy of player 2, meaning I'll fix a column, and from that column I'll go for the objective. So I'll maximize. So if I'm maximizing in column 1, I'll get 5. If I'm maximizing in column 2, I'll get 4 as the utility, and in the last column I'll get 5 as the utility. So this is done from the perspective of player 1. Now let's do it from the perspective of player 2. Player 2 would fix a row because he can't change the strategy of the other guy. So he's fixing that row and he's finding which of these is the minimum possible value. So from row 1 the minimum is 3, from row 2 the minimum is 1, and from row 3 the minimum is 2. So what happened here is we couldn't find a Nash equilibrium, at least not in pure strategy in this example, which fits with what we knew already. If the security levels of the two players are not matching in a zero-sum game, there won't be a saddle point. And if there is no saddle point, meaning no player would want to stick to any given strategy. At any point of time, they would want to unilaterally deviate. So we'll not find a Nash equilibria in such a case, which fits exactly into what we were looking into. Okay, any questions or doubts here?
Essentially, what you did is in the above matrix, you flipped the like player 1 is trying to maximize instead of minimize, and player 2 is trying to just minimize instead of maximize. So you flipped the objectives, right? So that's what you did.
Not exactly. So see, when I was looking at security levels, for example, let's say I was looking at the security level of player 1, I was not looking at utility where the strategy of the other guy is fixed. I did not look at a column. I looked at I looked at this. I looked at any one row at a time, meaning I fixed player 1's strategy, and I looked at if player 1 played, say, row 1, what are the different things player 2 could have played, and which is the worst of them.
Okay.
So it's not exactly opposite, it's a different way of looking for a stable point or looking for a solution of the game. All right, are you clear, or do you have any more questions on that?
And now I think it is because what you are doing here is like you choose a minimum here, like a minimum of first row is 3, minimum of second row is 1, and minimum of third row is 2. So you have added these minimums on the side. But because earlier you choose the maximums and then you choose minimum out of it. Here what you did is you choose minimum and then you choose maximum out of it. That's what I was asking.
Yes. Okay.
Okay.
Okay, so you can think of this, you can think of it this way. You can say, okay, security level is similar to saying that the objective of player 2 is to minimize. So which of these is the minimized scenario? But ultimately, after we have done that for each row, we are interested in coming back to the objective of player 1. So the idea is different in security levels and Nash equilibria, but they do end up having common points.
Okay.
Okay, so far we have taken 2 examples, right? Let's go further. Now let's look at the following. So now this is the relation between the security levels. Let me remind you again. Now I am back to the original convention where player 1 is minimizing and player 2 is maximizing. Hence, security level of player 1, it's first maximizing from the columns and then it's minimizing from the rows. And for the opposite agent, it's the opposite behavior. So now there's a lemma which compares these two. What can we say about these two cases? And it says that the security level of player 1 is always greater than or equal to the security level of player 2. And this is more of a property of the utility matrix itself. And this is how they went about the proof. Do people want me to go through the proof of this, or okay?
I think the proof was covered quite detailed in the lecture itself, so I don't
was
think reiterating that will make any sense if others agree like this.
Yeah, even I don't prefer going through proofs, but this becomes important if you have to do it for the opposite scenario. So you should be able to do this even if the objective of the players is interchanged. That's all. Okay, so just remember, in the convention that we are working with, security level of player 1 is always greater than or equal to the security level of player 2. Okay, next is defining a saddle point. So now let's say there are some strategies I star and J star for the players respectively. If there is a pair like this such that this property holds, meaning if you keep the column fixed, changing the I from I star to any other I makes the utility greater. Okay, or in the opposite scenario, keeping the I same, meaning keeping the column fixed, changing the J reduces the utility. So in one direction, this is the opposite of what you would expect from player 1, because player 1 is trying to minimize, and in this direction the player 2's objective is at play here, who is originally trying to maximize, but what happens here is in the saddle point the opposite behavior is visible, meaning this point or this strategy is somewhere sort of in between, and hence it is called a saddle point. So we can look at the example that we had above, example 1, and identify whether the security strategies that we got, or just some strategies that we got, does that satisfy is it actually a saddle point or not. So for us that strategy was this one, or I star was 1 and J star was 2. Oh no, sorry, I wrote it opposite. Corresponding to this 3. Okay, I star, no, not this example. I star is 2 and J star is 1. This is the example that I'm going through again. So now let's check if this strategy is a saddle point or not. Okay, so what we have to do here to check whether it's a saddle point or not, so let's take that particular one. So we have A21, and A21 is to be compared with this case where we are fixing the column. So we are fixing one, we're sticking with just one column, and we are changing the row. So we'll look at row 1 and row 2. So it's 1 1 and 3 1. So we're comparing 3 with 4 and 5. And we want whatever we have chosen to be the minimum one. And that's exactly what happened here. What we have chosen is 3, which is less than 4 and 5. So half of this property is satisfied. So this side of it is satisfied. Now, same thing, but we have to look at this side of the property. So for this side of the property, we want to check if fixing the row, so this time fixing the row means we're looking at this portion and changing the columns. So we look at A22 and A23. Whatever we have chosen, is that the maximum possible there, or maybe equal to? And we can see 3 is greater than or equal to 3 or 1. So this is a saddle point. You can, the exact same thing that we did here. So this is looking at, this is our chosen strategy. This is the utility of that chosen strategy. We are comparing whether this is the least one in that given column, which is looking at the objective of player 1. And then we are also verifying if this is the maximum in that given row, which is maximizing for player 2. So if such a scenario happens, if there is a strategy of this kind which has this double behavior, one side it is the maximum and in the other direction it's the minimum, if that's what happens, then such a strategy is called a saddle point. Okay, so now the reason for doing all this is because there is a theorem which says that if this security levels of the two players match exactly in value, then that matrix has a saddle point. It can have more than one saddle point also, there's nothing against that, but it has at least one saddle point. That's the claim of this theorem. And then since there is a saddle point, it's the security strategies that would have been used. So this is sort of comparing the idea of a saddle point with the security strategy. So what happens in this scenario is the saddle point is comprised of the security strategies themselves. And even the converse is true, meaning any pair of security strategies in such a game would form a saddle point. So what this process is telling us is, if in a particular example, let's say this one, we see that V1 and V2 are equal, or the security levels are equal. It didn't happen in this game, but in this example it did happen. If the security levels are matching, then the security strategies would likely form a saddle point, this one. And saddle point meaning neither player would benefit from in moving away from that. Both the players have
saddle point can be considered as a Nash equilibrium as well.
Exactly.
Okay, thanks.
Okay, so this is what this theorem is saying. This is giving us a way of going through a matrix game or a zero-sum game, calculate these security levels. If the security levels match for both the players, then we know that there is a saddle point that exists, and the strategy profile for that would be the security strategies. In fact, there are two corollaries that take it a little further. Okay, let me come to the corollaries first. They say if there are more than one saddle points, the value of those saddle points would still be the same. Value meaning the security level value. And if there are, more than one saddle point, so suppose there are two saddle points, it's this and this, then the strategies themselves can be interchanged. So I1 with J2 is also a saddle point, and J1 with I2, or I2 and J1 is also a saddle point. So this sort of tells us how we can find saddle points in zero-sum games, or how we can find Nash Ekpija in zero-sum games. Okay. Now a little bit of interpretation. If the players could play this game in order, like I played first, and then after me, player 2 can see what actions I took, what strategy I chose, and then he's supposed to decide his strategy. Knowing that that's how the game is, the best thing for me, for the first player, would be to play a safe strategy, which is this security strategy. Because the first player, needs to ensure that he doesn't get, for example, the max payoff. If the first player is the minimizing one, he would want to ensure that he doesn't get the max one. So what he would be doing is, he would be trying to play the security strategy, which would be keeping in mind choosing an eye such that this is the least possible worst case scenario you could end up with. And once that happens, player 1 has chosen its eye, player 2 would just play a strategy just based on the exact form of the game. He knows what player 1 has chosen, so he'll just take the best for himself from the options available and go further with it. So this is in some sense saying that the game got reduced. So player 1, suppose, is the one who's choosing first, and these are the two options. And player 1, while choosing, chose the safer option. Say this is the safer option, and player 1 chose this. Player 2 is ultimately just going to look at which of these three value has the maximum utility, and he'll choose that strategy. So that's a kind of a reduction of the game itself. So you can see that if this game was played one after the other and the result was visible to the other player, meaning it's not a simultaneous game anymore, in that case, security strategy or security levels serve as the best case or the best response. Player 1 would know or would expect rationality from player 2, and hence would expect that he would choose the best case scenario for himself, which is he would try to choose the maximum utility, whichever strategy gives the maximum utility. And knowing that, player 1 will choose a strategy such that he doesn't end up with the worst of scenario, which is he chooses a security strategy. Okay, so that's one interpretation of this particular game. Now, if the players are not supposed to be playing in order, if it's actually a simultaneous game and it's not that whatever I've chosen is revealed to the other one, then playing security strategies may not always be enough. We already saw an example where there was no saddle point. We see another example here. So if nothing is said, player 1 is minimizing, player 2 is maximizing. Then the security level for player 1 is to maximize from the column. So he says this is 4, this is 3, this is 2. So he's now ultimately supposed to choose the minimum from these. So 4, 3, 2, he chooses 2. And that ends up being the third row. On the other hand, player 2 would want to minimize from each column. So he would choose from 4, 0, 1, or from first row he would choose 0. From the next one he'll choose -1, and from the last one again he'll choose -1. And player 2 is ultimately maximizing, so he will take the maximum of these 3, which gives him 0. And hence for him the column is the first column. So this got chosen and this got chosen. But here these two are not matching with each other. What does that mean? So let's just look at player 1 for the time being. So player 1 is told, as per security strategy, that he should play or choose row 3. If he chooses row 3, what would player 2 do in this particular scenario? Player 2 is supposed to maximize, so he has these options 1, 2 and -1. He's going to
Second column.
choose, yeah,
Second column.
so he will choose column 2, meaning the best response to row 3 is actually column 2 and it is not column 1. If the security strategy of the other one is not a best response, the player would want to shift, which is what would happen here. If we look at it in the opposite way, which is if player 2 chooses player 2 chooses column 1, meaning this is all we are left with, then player 1 who is minimizing would choose row 2 and not row 3. So again, for the security strategy, the best response is not the security strategy of the other one, it's something else only. So in general, the point here is, in general, security strategies do not mean that they will end up being a Nash equilibrium of the game. Rather, we are supposed to look at the security levels. If the value of the security levels match, then we can expect the security strategies to be Nash equilibrium or a saddle point. But in general, that will not be the case. Okay, and then these are two corollaries. We already talked about them. These just say that suppose if in a game there are more than one saddle points, then for all of those saddle points there'll be this security levels, and the value of these security levels will be the same no matter which player we're talking about or whatever it is. And lastly, the saddle points are interchangeable, which is this. Okay, any doubts so far? Okay, so now let's so far what we had assumed throughout was, or the examples that we took were mostly in the case with finitely many pure strategies. So now let's take a very specific example where the players are actually taking more interesting choices of strategy. So now it's something of this kind. So let's say there are 2 players and they're supposed to choose x and y from an interval of 0 and 1. Player 1 is maximizing and player 2 is minimizing, so it's opposite of our convention. And we are given a utility function, and this is the utility function for player 1. And we are supposed to find out if there is a value of the game and if there is a equilibrium of the game, or if there is a saddle point of the game. So we're supposed to repeat all the same things. It's just that the only difference is, because everything is continuous now, we can use properties from calculus and all that and find these min, max and max mins. So if you want examples of this kind, there are many such examples in the book by MSZ. Examples and even exercise questions if you want to try these out. So I'll take just one of those. So let's say this is the particular utility function that we are given. And we are supposed to calculate the security levels for both the agents and find out what is the value of the game. Okay, so let's start with the security level of player 2, meaning we are focusing on we're looking at the security level of player 1 for the time being. Anyways, we are looking at V dash. So for that, what we first are doing is we are minimizing with respect to Y and then maximizing. So this is for player 1. This is for player 2. Okay, so we are supposed to minimize this function with respect to Y, which is in the range of 0 to 1. We could rewrite this by taking terms that have by dependence together and the remaining terms separately. So now the value of x has a role to play here. The value of x will decide whether, or rather this would behave like a slope and tell us what will happen or how should it go about. So if x is greater than or equal to 1/4, in that case this would be positive, and since we are minimizing, we would take y to be what would we take y to be, 0 or 1? It's supposed to be 2x plus 3. So in this case we took y to be 0, and in this case we took y to be okay, right, yeah. Okay, so next step so that we can find this v hat is to maximize over x, and we're supposed to maximize this quantity. So if you do the maximization, You could just make a small plot of this and also check with that. If you were to do the maximization, you'll see that at x equal to 1/4, there's a unique maxima for which the value of this is minus 1 by 2 plus 3, which is 2.5. Okay, if we repeat the same process for the other agent or the other player, we would be looking at v bar, which is min with respect to y, and then max with respect to x for this uxy. So max with respect to x of uxy is this 4xy minus 2x minus y plus 3. And similar arguments as above. This is linear, so we can just take things with respect to x together. That is 2y minus half. Now it depends on what is the value of y. If y is greater than half, then this quantity would be positive, and if that is the case, and we are maximizing, so it is helpful to take x to be 1, which tells us that this would reduce to 2x. Oh, this would reduce to or that is in the case where y is less than half, this would be negative. 0 or 1 here would mean that 1 here would mean that this becomes even more negative, and this would reduce the value, so we'll let it be just this, meaning x is 0. So this is minus y plus 3, and ultimately this quantity would be minimizing over y of this whole quantity. And this turns out to be again 2.5 at y equal to half. So now you can see again these security levels are matching in value. So whatever we got as the security strategies, that will form a stable point. So this is the value of the game, and y star equal to half and x star equal to 1/4. These form the saddle point together. So whatever we studied can also be applied to scenarios of this kind, at least in a unit square type of a scenario. We can apply the idea of security levels to find a saddle point or to find security strategies for that. Is this okay? Any doubts so far?
Everything is clear. It's perfect.
Okay. So next we look into another type of strategies which are called as mixed strategies. So far we referred to as, so in this example, just the value of x and y, the exact value of x and y between the interval, referred to as a strategy. Those were infinite, so that's a different scenario. But otherwise, in most of the previous examples that we talked about, or throughout this session, we took the case where a strategy was just choosing a row or a column. A row chosen by player 1 and a column chosen by player 2. So those were examples of pure strategies where only the players decided to play only one row or a column respectively. On the other hand, there are strategies where the players can decide to allocate resources in some example. In, say for example, if suppose there is a war to be taking place between two countries, and the strategy is where should they place their troops. Should they place troops at location 1 or location 2? And both of them are supposed to figure this out on their own, and that will decide what happens to the result of the game. So one solution, that the kind of solutions that we have seen, is send all the troops to area 1 or send all the troops to area 2. That's the kind of strategies that we have so far. But they can always find a fraction, send a fraction to location 1 and send the other fraction to location 2. So suppose if they had, let's say, an army of 1 lakh soldiers, so one particular strategy could be to send, say, 75,000 of them to location 1 and the remaining 25,000 to the other location. So a splitting of this kind, or a randomization of strategies, is what is referred to as mixed strategies. So this is just done by putting a probability distribution on top of it's here. This is just putting probability distribution on the space of pure strategies. So if you've seen in our previous example, say okay, maybe I'll take an example here. So suppose it's a zero-sum game of this kind. Player 1 is minimizing as always. Then instead of just choosing one row, I can say, let me assign a probability to each row. So let me say I'll choose row 1 with some probability p, and hence the other row would be chosen with probability 1 minus p. So now this becomes the strategy of the first player. So what I've done here is, for each pure strategy, let's say there are m pure strategies, I've assigned a probability for each of those i's, and the assignment is such that it satisfies the standard properties of probability. So yi, all of these are greater than 0 for all the i's belonging to 1 till m, and the sum of all of these has to be 1. So it's starting from 1 to m. And similarly, I can do that for the other agent also. So for the other agent, maybe instead of having p, I can have q1, q2, and 1 minus q1 minus q2. So this way, now the strategy space has expanded from just taking one row or one column. It's saying by what fraction we are taking a particular row or a particular column.
And these probabilities are prior probabilities or posterior probabilities, like these probabilities that we have in mixed strategies. These are static prior probabilities.
Yeah. So there's no concept of a prior or a posterior at this point, because all we are saying is for a given pure strategy, I'm just assigning a probability on top of that.
And these probabilities are static, like they don't change.
Oh, so okay, so what is actually happening in all of this is these probabilities don't have to have a fixed value. We are going to search for the best possible value of p, q1 and q2, which gives us, which allows each agent to reach their objective in the best possible scenario, best possible way. So p1 would be able to minimize the best, and the other player would be able to maximize the best. So which of those probability values, say p or q1 or q2 or whatever, which of those values do that, those will be the optimal mixed strategies. Mixed strategies just means that q1, q2, p can have any values they want, any probability values they can have.
So is there any correlation between this thing, like mixed strategies, and the belief systems that we have learned in week 2? So in belief systems, we learned that the prior probability that we assign updated based on the observation of events. So is there a remote correlation between that thing and this thing? Because what you mentioned is we calculate the probabilities, optimal probabilities. So is
Okay, so in the Orman model with belief, the probabilities were on the state of the world.
okay.
Here the probabilities are in choosing the action. So these probabilities are a tool available or a resource available to the agents.
Okay.
This is part of their action. So they're very different things.
Okay. Thanks, man. Thanks.
Yeah. Okay. So we could write it in a slightly more formal way. So the set of strategies, let's say for player 1, would be this Y strategy with, if it is M, a total number of rows available are M, then for each of them there'll be a probability value assigned such that it's all of those values are greater than or equal to 0, and the sum, and they all sum up to 1. So that kind of all such Y's would form the set of mixed strategies for the row player. And similarly we can define it for the column player also. So let's say there are n columns, so we'll define probability for each of those columns, and those have to be actual probabilities. So the set of all those strategies would now be the strategy space for the column player. Now because we have randomization for the strategies, the payoff themselves will also have a randomization involved, or we'd be now looking at the expected payoff. So the expected payoff would be this guy. This is aij yi times zj. So we're looking at the particular utility value, and we're looking at what is the probability assigned by each of those agents for that particular strategy, for that exact ij profile, and that gives us the expected payoff or the expected utility for that particular case. So we could look at this example and try and calculate these things. Let me simplify a little bit. I don't want to deal with 3, so I'll just remove this last column, or maybe not. Okay, let me take another example then. Okay, so there's a probability assigned to this. The other one will have just probability 1 minus of that. Let's say this one has probability q, and this is minus q, 1 minus q. This is player 2, this is player 1. So what I've done is I'm saying the strategy space for player 1 is now this p and 1 minus p, where p itself can take values between 0 and 1. And similarly, z is q and 1 minus q, where q itself can take values between 0 and 1. By the way, the reason I have put closed brackets is because p can take 0 value or 1 value. If it takes one of those values, then what we'd be left with would be a pure strategy. So suppose if p is 0, then that means we are choosing row 2.
So
That
basically,
becomes a
this is
pure
an
strategy.
interval. It's a closed interval where like we can have 0, 0.2, 0.6, something like that, right?
Yeah, exactly. So then the expected payoff for a choice of p and q would be this A by transpose Z. Okay, if you want to do it more carefully, you could actually calculate it and find out what that is. So this is, we're taking it to be P1 minus P. You could write this out cleanly if you want. So this gives us the expected payoff for a choice of P and Q. Now if you change the value of P and Q, the expected payoff changes. Right? So that tells you, that at least suggests, maybe it doesn't tell you right away, it suggests that we can use the same kind of arguments that we had so far. We can look for either dominant or dominated strategies, or we can try and look for these security levels and so on, and try to find stable points even with mixed strategies. But anyway, doing that is something that will be covered in the next class, so I'll not go through that part yet. But at this stage, you can still write down what is the expected payoff for a choice of P and Q, and that choice tells you in which direction it should move, roughly where the minima would lie, and all of that. Now if you look at that example that I did right before this, the example of finding xy on that square matrix, on the unit square, this is now very similar to what I'm saying. This is a much simpler scenario where everything turns out to be linear, you can think of these x and y's are a kind of a probability choice only. But the utility function is given to you in a functional form here. On the other hand, here we are given it in the standard matrix form. But nevertheless, we can still argue in very similar manner. So I'll skip those arguments for the time being. Anyways, so any doubts so far? Okay, let's continue. Now, after we have talked about what a mixed strategy is, what does it mean to even create these mixed strategies for any given payoff matrix and get the expected payoff, next thing would be to try and solve for it. But to be able to solve for it, we need a few more definitions. We need to go to the next part, which is the security strategies. So again, it's the exact same idea as we had before. Earlier, what we had was, suppose we were looking at player 1. So for player 1, the idea was to maximize Aij and find the strategy I star, which in this maximization process still gives us the minimum possible thing. That's the exact same thing that's happening here also. This was for row column players. Now, we would define it in the following way. We are looking at the expected utility. Here we were looking at the utility itself, but now utility on its own doesn't have any meaning. It's the expected utility that we are supposed to look at. And we are maximizing over the strategy of the other guy. So for us, the other guy is player 2, and player 2 strategy is denoted by Z. So that's what we are maximizing over. And we are saying the strategy Y star is called as a security strategy if it is the least that we could do from the worst case scenarios. And that would give us the V bar. Since we're talking about mixed strategy, so VM bar of A. Similarly, for the other agent, we could define it in terms of minimization. It's minimization with respect to Y of this quantity of the expected utility, and we want to find a Z star such that this minimization is the maximum possible that we can find, and that gives us the security value for player 2. So this is for player 1 or the row player.
And the value, this mean security, this what we say, like the V with overhead line and M, this one, okay, and the pure security strategy. This is basically the mean strategy, I guess, and the pure strategy. Pure strategy will always be bigger than this one. Like, why exactly this?
We're coming to that.
To be sure.
This is row player, this is column player.
And is this distinct, like this VM is distinct, or we can have multiple of them based on priority distribution across the space?
See, just like we did in case of a normal matrix, we got one value. Once we have finalized on how to maximize over Z and what Y star to choose, this and this is fixed. This is also fixed. So this is going to give us one value at the end. The same thing happens. If these two values match, then ... there'll exist a saddle point and so on. Anyways, we've in the lecture also, sir didn't get to that point, but it'll come up in the upcoming classes. So now next thing was to sort of compare these, right? We already have seen what happens if we are talking about the original players. If you're talking about the row player and the column player, if they were playing pure strategies, what happens? And we have seen the comparison between these two. It's the V bar, this one, that will be greater than or equal to the V dash. We would expect something similar happening here also. So this is the relation that we would expect.
Is it so in every single situation, like because this is somewhere in the same interval between the pure security strategies. So basically, it will always be like yes, this is the for one for player 2 it will be always lower than for player 1. Probability strategy.
It's defined in that way. See, player 1 is minimizing,
Okay.
and hence whatever security level he will get will be a higher value than what he would genuinely want to get. He'd be like, okay, I don't want something more than this. Hence his value would be on the higher side as compared to the other guy who's actually trying to maximize. For him, the security level is somewhere below. So that's pretty much the gap. Okay, so now the next thing would be to try and see what is the relation between all these four of them, where this one is with respect to pure strategies. This is with respect to mixed strategies. So the ultimate comparison is between. Okay, I've not included anything further. The ultimate comparison is in between these two. And this can be argued in a slightly hand-wavy but easy way is by just looking at the set of strategies. Whatever was possible with pure strategies is possible with mixed strategies by default, because mixed strategies are a superset of pure strategies. So with mixed strategies, we would be able to get a better security level, meaning the security level which was here, let's say for player 1, it would reduce and would be slightly lower for the same player. And that's exactly what this correlation is saying, this inequality is saying. Or in other words, I could make a little diagram here. So if these are the security levels, this is the security level of player 1 who is minimizing, because he's minimizing whatever is like, this is the worst that I'll get, this is the best of the worst that I can get, that's this V bar level. This is for the other guy. Now we know whatever is possible with pure strategies is definitely possible with mixed strategies. In fact, mixed strategies would be able to do better than that. And hence, the relation between those two would still be the same. So Vm hat of A would be higher than Vm bar of A. But this is the next thing that will happen. With mixed strategies, we'd be able to, in general, we'd be able to get better stability also, or better security also.
One last thing that I want to ask was, like in the lecture, it was mentioned that in mixed strategies are more general than pure strategies. What's the meaning of this general term?
Okay. So see, mixed strategies means we can write any one of them. So like Y is this, right? Let's say we are restricting ourselves to just 2 rows. So I could write it as P, 1 minus P, right? And this P and P minus 1 could take values between 0 and 1. Okay, so one possible strategy here is this Y, rather this small y that belongs to Y, can be 0, 1, right? So this is row 1, this is row 2. And this strategy is saying what I've actually chosen is row 2. I could have also had a scenario where P is 1. So the probability distribution would be 1, 0 on the 2. And that means I've actually chosen row 1. Now these are the pure strategies. And the way mixed strategy is defined already includes these pure strategies. So mixed has these pure strategies and more. That's why it's more general, or this is a superset.
Pure strategies are also mixed strategies, but mixed strategies are, yes, opposite. So pure strategies are a subset of mixed strategies.
Yeah. Pure is a special case, right? It's if I take specific values of P equal to 0 or P equal to 1.
It's fine.
Or if, this is a simpler case, like I've taken only 2 rows. You can take n rows. For n of those rows, only one of them is 1 and everything else is given a probability mass of 0. If that happens, that's a pure strategy. But if you're writing it in the form of a mixed strategy, that means you've just written it in a general way, but it's a pure strategy anyways. So in that sense, mixed strategy is more general or a superset of the set of pure strategies.
Got it.
Got it? Okay. So, okay, with this I've covered most of the things that I wanted to cover. So I'll just take a quick summary. If you have any doubts, you can ask.
It's a little bit embarrassing to see like you're spending 2 hours of effort in doing this, and we have like just one person is there on the call like that at the end.
I'm not surprised with that. That's very common. Okay, so today we talked about zero-sum games. We talked about the scenario where there are 2 agents and the utility of those 2 agents is just the opposite sign for both of them. So all we are left with is looking at the utility of one of them. Typically, the standard convention is we look at the utility of one of them, of player 1, and any particular element in this matrix, for example Aij, refers to the case where player 1 has chosen row I and player 2 has chosen column J. We commonly take the convention where player 1 is minimizing and player 2 is maximizing. Keep this in mind, otherwise you will get confused in assignment questions. I've been repeating that a lot of the times. Okay, then we know that there are no such properties. There are no properties of this kind, at least, on the matrix A. Matrix A can have any number of rows or any number of columns, and the entries don't have to be positive or negative, they can be anything. Then we took an example to see what is the meaning of strategies here. Typically, when we are choosing a strategy, we are just, any agent, when they're choosing a strategy, they're just looking at trying to get the best of their objective. So if they are minimizing, they'll try to just find a strategy that minimizes the most. But that may not always be possible. There may not be even a dominant or a dominated strategy in certain games. So in those scenarios, it's possible that player might want to ensure they don't get the worst outcome. They want to reduce the chances of getting the opposite of their chosen outcome. In that case, the choice of strategy that they should go for is called as security strategies. So in security strategies where player 1 or the row player is minimizing, he would want to try and see and find a strategy such that if the other guy maximizes the utility, if the other guy maximizes the utility by finding a particular strategy, then the choice of I should be such that it's the best out of the worst possible scenarios. And such a I star is what we call as a security strategy, and the value of this minimum of this quantity is what is called as a security level or a min max. Similarly, for the other agent, we define it as a max-min. Then we took a few examples where we saw, okay, this was a very elegant example in the sense that in this example we found that the security levels of both of them actually coincided, and the security strategies ended up being a Nash equilibria, meaning it was also a stable point. And
And one question on that particular, the three, oh, yes, this exactly. Sorry for interruption.
No,
but
no problem.
we found the Nash equilibrium is 3. Okay. So all the values of 3, like, no, it will not be like
No,
that.
no, no.
Yeah,
It
I
doesn't say
thought-
that.
I thought that there are multiple Nash equilibriums because I saw 3 multiple times. Then I observed, okay, no,
There's only one.
Only one is there. Yeah.
There's
Sorry
only one.
for the interruption.
In this example, at least, there's only one. There might be in other general scenarios.
In assignment, there is a question associated with the same thing. That's why, because they have multiple Nash equilibrium, one question is there.
It can happen. Multiple can happen. This example has only one. Okay. The other scenario is if the security levels of the two agents may not match, and if that happens, there won't be an equilibrium or there won't be a saddle point. Then we looked at the comparison between the two security levels, and in general you can think of it as the security level of the first agent, the one who is minimizing, would be always higher than the security level of the other agent who is always maximizing. This is what the players are doing. And we saw what a saddle point is. A saddle point is something that satisfies this property. Any such strategy which satisfies this property is called a saddle point. And the example that we saw above had that exact thing. The security strategies there satisfied the property of saddle point. Now, make sure you understand this much. At no place we are saying that a security strategy would always satisfy saddle point property, because saddle point property is something that is related to the behavior of the utility for both the agents. It's not just one. Yeah.
So in lecture, it was mentioned that saddle points always occur in pairs. Okay, and security strategies are like they don't occur in pairs. They can occur like individually in the entire matrix.
Yeah, because when we are looking at security strategies, we are looking at each agent's utility. We are not making a comparison of this kind. We are making a comparison either on this side or on this side. Saddle point is something that wants both of these sides of the condition to be satisfied, not just one, for one strategy pair. So that one strategy pair is the key point when we talk about saddle points. So all of this, the example and the theorem, that basically ultimately says that if the security levels match, then the matrix, the game, will have a saddle point, and that saddle point will be basically the security strategies. And in fact, in such a scenario where these two are matching, the security levels are matching, any security strategy would form a saddle point. This is related to the interchangeability point also, the interchangeability corollary that we saw. Then we saw a couple of more examples, and then finally these corollaries, which says all saddle points will have the same value. By value, I'm talking about the security level values. Even if there is more than one saddle point in a game, in a particular matrix, you'll need a bigger matrix for that in general, then the value would be the same. So whatever we got here, these V's would be the same for each of those. And if there is more than one saddle point, then there is an interchangeability. You can interchange the security, you can interchange the strategies between the agents. That increases the number of saddle points basically. Then we saw an example where the strategy choice for the two agents is on a unit square. we repeated the same process. We looked at the security levels and we found out if the security levels are matching, then whatever strategy did that is the saddle point. Now, this example, in other words, is basically giving the hint for the next topic, which is mixed strategies, where we say that each player is choosing a row or a column with some probability, and that probability has to satisfy standard properties, which is that it should be greater than equal to 0 and it should sum up to 1, and this forms the set of mixed strategies. So in pure strategies in general, what we saw, except the last example, there were a finite number of strategies, but here these yi's can take any value between 0 and 1, meaning this forms an infinite set of strategies. So the space of strategies has now expanded to infinite in this particular case, and similarly for the other agent. Now, earlier, since we were choosing only one strategy, either a particular row or a column, so we were focusing on the utility function itself, the utility value itself. Now, since there is a probability assigned to it, so with some fraction it's the choice of any particular row or a column. So
Earlier
what
it
we
was
would be,
discrete, now it is continuous. So because of being continuous, it can have infinite combinations possible.
yes, perfect. So hence we talk about expected payoff. So the next definitions, which are the security levels and so on, for mixed strategies would be based on these expected utilities. Remaining, it's the same. Earlier, we were looking at max, for example, if it was the security level of player 1, we were looking at the max of column. Here, we'd be looking at max of strategy Z. That's it. Why did I put a question mark here? Okay. Oh, okay. The question mark was just to remind that this is yet to be fully discussed in class and proven. Then we saw that these security levels that we get in mixed strategies would typically be an improvement on the security levels in the pure strategy game. Yeah. So the next tutorial would be more about mixed strategies and how to calculate them and how to find the equilibria concept and so on. Okay. Any doubts?
Oh,